Okay, in this video we're going to talk about what happens when you see the words and or in a probability statement. In probability we usually refer to these terms as intersection and union, but they mean the same thing. And means intersection, or means union. So in these examples, this is going to be a slightly longer video, but we're going to be using these same definitions. What's happening is we're going to draw a single card from a deck of 52 cards. You've seen this example before. The sample size S is all 52 cards. They're all within play. We have three events that I've defined right here. Event A is drawing a heart. Event B is drawing a face card. And event C is drawing a spade. So let's talk about A and B. What if I asked you, what's the probability of drawing a heart and drawing a face card? So we'll say A and B. I'm going to use a different color pen here. Let's go back to black. A and B. This is drawing a card that is both a heart and a face card. A and B. And so we call this the intersection of A and B. And I'm not big for symbols, but this is going to come up a lot. In probability, you would see this written as A upside down U, B. That means the same thing. A upside down U, B means the intersection of A and B. And again, what we're saying here is A and B means you have to draw a card that is a heart and a face card. And so the probability of A intersection B is going to be equal to, well, let's just think about it. How many heart face cards are there? There's the Jack of Hearts, the Queen of Hearts, the King of Hearts. So that is going to be 3 over 52. That just makes common sense. Let's take a look at this graphically, just for the heck of it. If I do this right, I'll draw the event A, which is drawing a heart, should be bigger, and drawing a face card should be, well, it's actually almost the same size. Of course, I drew it bigger. Drawing a face card is slightly smaller. There's only 12 face cards, so yeah, sure, that works. And what we're really interested in here, let's see if I can fill this in correctly, it's sort of a toss-up, is this space right here, the one I missed. Okay, you know what I'm going for. It's this little area right in the middle. That's the intersection. That's a heart face card. Right there, the intersection of events A and events B. So, intersection. All right, so now I want to look at another example. Instead of A and B, let's talk about A and C. Let's leave these up here. A and C, and let's think about what that means for a second. Well, obviously it means the intersection of A and C. And in real world terms, that means you have to draw a card that is both a heart and a spade. And that doesn't work. You can't draw a card that is both a heart and a spade. A card is either a heart or a spade or a club or a diamond. No card can be both, and we're not talking about jokers here, so don't even think that. What we call this, when there's something that can't exist, it's often, I got a little bit aggressive with that line that went through, but this is the symbol for the null set. Same thing. Come on. I can do better than this. The null set. When you see this symbol here, often written without such an aggressive line through the middle, it means the null set. And that means that there is no possible outcomes that fulfill what we're asking here. So it would look something like this, drawn out. Up here, just to be clear, here we had A and here we had B. Now we've got A over here and C over here. They should be the same size, and they're close. There is no intersection, absolutely no intersection at all. Therefore, there's nothing, like up here we had a little something that could have fulfilled our requirements. For A, the intersection of A and C, nothing fulfills our requirements. Therefore, we get the null set. So there's another concept I want to put out there now, and it relates to this example of A and C leading to the null set, having no possible outcomes associated with the intersection of those two events. And that is the concept of mutual exclusivity. When this happens, we say that A and C are mutually exclusive. And that means that the intersection of A and B don't intersect. There is no intersection between, A and C. There is no intersection between A and C. That means they are mutually exclusive, and the graphical representation looks like this. No overlap, mutually exclusive. And get ready for a really profound statement. But, I think it might be important to keep in mind. And that is that all events, and anytime you take two events, or more than two events, they're either mutually exclusive, meaning no overlap, or they're not, meaning they do have some intersection. So all combinations of events are either mutually exclusive, totally separate, or they're not. They have some intersection. All right, enough of that. Let's move on to a new page and talk about OR, as it is related to probability and multiple events. All right, so we're back to this example again. Actually, let me grab this and move it up a little bit. So talking about OR, we might say something like A or B, for instance. And that would mean drawing either a heart or a face card. And when we talk about, and this is represented, so this is represented as the union of A and B. It's just a fancy term for OR, just like intersection was AND. Union is OR, union of A and B. And it's represented as AUB. Make a cheat sheet on this now. I don't know why, but when I was learning probability for the first time, I had a heck of a time keeping this. Okay, this is union, and this is intersection, straight, meaning this is AND, this is OR. I guess one way you can think about it is, if you can remember that union means OR, the right side up U could stand for the union, and that might make it easier to remember. Write it down, make sure, make a note of it in your phone, I don't care. Just get that symbology straight, or else you'll be confused as you do your readings in your statistics class or what have you. All right. When we talk about probability, I actually want to shift our example here, and I want to talk about the probability of A or C. So I'm going to go ahead and actually erase what we've got here. You know what? I don't want to do that. I'm going to leave it up there. We're just going to start a new line. Probability of A or C. Just recognize that I'm shifting examples here. Now I'm talking about A or C, meaning what's the probability of event A, drawing a heart, or drawing a spade? In a single draw from a deck of 52 cards, this, what we're talking about is drawing either a heart or a spade. It should make sense, okay, that makes sense. The reason that we're shifting to this new example is because finding the probability of a union is really easy when the events are mutually exclusive. As we established on this last page, we said this is A and C. A and C are mutually exclusive. You can't draw a heart, you can't draw a card that is both a heart and a spade. And when we're talking about probability, it's really easy to determine mutual exclusivity. Now, this should be very obvious. First off, we can just think about this and say, okay, there's 13 hearts, there's 13 spades. If I'm going to draw one or the other, that's 26 possible outcomes over 52. That's going to be 26 over 52. And what we just did, just thinking through it in terms of common sense, is exactly what you would do in terms of the calculation. When events are mutually exclusive, you can add together their probabilities. So add probabilities of mutually exclusive events. And so this would just, you could also have written this as 13 over 52 for the chance of getting a heart, plus 13 over 52, which is the chance of getting a spade. This would be A, this would be C, and that comes out to the same thing, 26 over 52. Same thing we got by just thinking about it using common sense. Representing this graphically, here's our sample space S, all 52 cards. This is, I drew those rather nicely. This is event A, this is event C. We're going to add them. That's it. That's all we're doing. We're just adding those two together. All right, so let's move on. I think I've used up most of the real estate on this page. Let's keep this here. And let's talk about, now we're going to go back to our original example and talk about probability. That's an ugly P. Probability of A or B. And these, remember, are not mutually exclusive events. There was intersection between A and B, meaning there are some cards that are both hearts and face cards. So, just to make a common sense definition here, when we say the probability of getting a heart, drawing a card that is either a heart or a face card. That's what we're saying here. We're saying, what's the probability of getting either a heart or a face card? And again, let's think about this sort of just common sense. Probability of getting a heart, we know, is 13 out of 52. There's 13 hearts. And now we have some other cards. We can also get a face card. And some of we've already kind of accounted for some of those face cards because they're already hearts. But there are some other face cards out there. There's 3 face cards. There's a Jack, Queen, King of spades. There's a Jack, Queen, King of clubs. And there's a Jack, Queen, King of diamonds. So there's 9 additional face cards. So if we add those all together, we're really just saying, common sense tells us there are 13 plus 9 over 52 equals 22 over 52 cards that are either hearts or face cards. And let's look at this graphically really quickly. That was pretty nice proportion. So this is A right here. I get excited about these things. And this is B right here. We know A is slightly larger than B because there are 13 hearts and only 12 face cards. And our intersection is the middle part right here. And mathematically, if we were to figure this out, not using common sense, but mathematically, what we're saying here is we would say, well, there's 13 hearts, 13 right here, and there are 12 face cards. And in the intersection, there are 3 cards that are both hearts and face cards. And the reason that we can't just add these 2 events together to get our total, the total number of outcomes we're looking for, is because we'd be double counting those cards that are hearts and face cards. Some of you are very familiar with this from a mathematical standpoint. For those of you who are not, let's just think about this really quick. if we're just going to count, we're going to have to count the hearts. And there's 13 of them. And there's 12 face cards. And the reason we can't just add them together is because then we'd be counting those three. We'd say there's ace through 10 of hearts, and then there's jack, queen, king of hearts. Those are the face cards that are also hearts. We counted them once. But then if we count them again with the face cards, we're double counting them. We only have 22 possible outcomes, meaning there's, however way you want to slice this, you could start with face cards and say there's 12 of them, but we can't count them again when we're talking about the additional hearts that we might choose. So there's only 22 possible outcomes. And so we can get to the probability here by actually doing this equation here. We say probability of A union B is equal to, and this is an important equation that you're going to want to write down, probability of A plus, I'm saying one thing, writing another, plus probability of B minus the probability of A intersection B. Because we don't want to double count it. We've counted it once here. We've counted the intersecting, we've counted the cards that are hearts and face cards once here. We've counted it again here. So then we have to take it out once. Because it's been double counted, and so now we almost about to flick off the camera. And so now we have we've counted it twice, so now we have to remove one of those counts to get back to sort of the realm of reality. So we say the equation to find the union of A and B, meaning probability of getting A or B, is probability of A plus probability of B minus the intersection of A and B. All right, one last challenge question for you all on the subject of mutual exclusivity. The question is this: are A and the complement of A mutually exclusive? If you need a moment to think about this, pause the video because I'm about to go into the answer. The answer is, of course. A and the complement of A are mutually exclusive. Of course, you remember that the complement of A means everything that is not A. So let's look at this graphically. Here's our sample space, S, and here's A. All right, that's A. And the complement of A, and actually let me fill this in so that we all are on the same page here. That's A. Here is the complement of A. And we'll fill that in as well with the different color. Is there any intersection between these two? Of course not. That's kind of the definition of a complement. There's no intersection at all. Therefore, they are mutually exclusive.